much. We'll talk about this later. And I'll now instead introduce our next guest, who's Francesco Capuano. Francesco Capuano does robotics at Hugging Face, so we'll probably look at this from a completely different angle. Francesco. He's also the IT guy.
Yeah, nice meeting you everyone. I'm Francesco, currently at Hugging Face, but I'm an incoming PhD student at Oxford. I'm starting next week. So, as someone who does work at an actual open source AI company, I don't have to say all the things that Julia said, but I get to share a bit of what we do with the library that we're building, lerobot, which is an end-to-end robotics library that we're developing at Hugging Face. And I want to start by the end of this talk. I want to convince you, and I want to try to convince you that what's happening right now in robotics is that we're building robots which are increasingly effective in real-world tasks. And this increasing effectiveness is powered by the fact that we're moving away from how we did robotics classically. This is something which is changing, completely old school. We don't want to do that anymore. What we want to do is use robot learning, which is leaving behind also reinforcement learning. So there's a shift inside of the shift. We're leaving something behind. We're embracing behavioral cloning as a technology that powers the new robotics revolution that we're living through. And then we are building large-scale models that do build on the technology of behavioral cloning and that are powered by having more robots, more data, and also increasing amounts of compute. And because we're doing all of this entirely open source, there is an end-to-end library which allows you to do everything, which is lerobot, and I invite you all to check it out. Even if you don't do robotics now, I wasn't doing robotics a year ago. Started looking at the library, and I can tell you that this is exactly super cool. So you guys want to check it out. This is what I want to argue, but I want to start from, this is the end, but let's start from the beginning. Robotics is complicated, right? Classical robotics has never worked well. This is the DARPA challenge in 2015. This was the challenge that assembled the best robotics researchers in the world that were tasked with solving one specific problem. Design autonomous robotics platforms that can go into extremely destroyed environments, including nuclear cataclysms. I'm talking about Fukushima 2015, and design robots that can get inside of a building, open a valve, close a loop on something, drive a car, climb stairs. None of that actually works. And it didn't work for the best robotics researchers out there. This is people that have been doing this robotics research for 20 years. So you cannot claim this is something new with the skills of the individual researchers. Also, the scale of the experiment is large enough that you can't claim that the people who were doing it, at least a fraction of them, were actually smart. But something is happening, right? Like, we don't see this anymore. Now we have a robotic platform which is able to do something that a few years back other robots couldn't really do at all, and this is loading a dishwasher. Now you guys might look at it and say, this is much simpler than helping humans in a nuclear facility cataclysm, but actually it's much more complicated because of the diversity that you have to embrace and all the things that you have to take into account when you develop this. And this is something which, sure, is powered by the fact that we're building better robots overall. Robotics is a multidisciplinary field. You have hardware, software, we're building better forms for sure, but that's not the only part of the deal here. I would argue that, sure, we have better hardware, but the main change is that we're using a different way to control this hardware, which is the software innovation, and also as a machine learning guy, I also have to say that's in this case. And the first key result, the first key thing that we want to discuss is that we should move away from classical robotics. Classical robotics means using multiple pipelines inside of a system that perceives states, plans using trajectory planning, controls them using low-level control or higher-level control. Like it does something that looks like a dynamical system control, which doesn't really look good because it's a multi-step process, which is just too complicated to all intertwine. And then you really have multimodality challenges because what happens when you want to extend to images? What happens when you don't want to use only gyro states, when you want to use images because you're having a robot that moves in the environment that doesn't have sensing of everything that happens, but you just want to use camera views, like in self-driving cars. And the thing which I believe is the most compelling is what happens when you don't have a really good understanding of the world. Now, I'm not a physicist, so I'm not going to claim much about it, but if you look at the last plot, that's a visualization of what a really popular model for friction, depending on angular velocity, meaning the friction that you have at the gripper. So when you're holding an object, if you move the object, how much friction is there? And that's a line, right? There's no way nature works with lines. So how do you reconcile the fact that the observed phenomena is much more complicated, but the models that we have of them need to be simplified because otherwise we don't have analytical understanding of them. And all of this is completely taken care of by robot learning. So we're completely moving away from this. We're not building multi-modular policies anymore. We do monolithic end-to-end, state to action. We don't decompose it anymore. Also, we don't really need to extract features by hand. We can learn that. We've proven that. I guess that if anything, Alex then proved that we don't have to engineer features. And then, yeah, we can forget about modeling. So we can just about modeling. We can use interaction data, and that should be just as good as modeling was, if not much better, because it doesn't rely on biases that you make on the environment evolution, which bias you towards getting you in some sort of like suboptimal state. This is the first shift that I want to talk about, moving away from classical robotics into robot learning. The second is that in robot learning, people have done reinforcement learning for the last 10 years. The first paper that talks about this is actually a survey paper, which does a great job at like understanding all of what we're doing here, and it really presents you with a, let's say, a slightly too good picture of what reinforcement learning can do for robotics. And mind that I'm a reinforcement learning guy. Like I come from that background, I believe in that. But we have a major issue. Reinforcement learning relies on the fact that you can have a simulator of the environment, and we don't really have that. We don't have a way of simulating high density, extremely complex, deformable object simulation. There is no way that we can simulate how this cable bends if I push on it. Nothing. And I guess that was part of the presentation. The second thing which we should think about is that reward functions are super complicated. Like you don't get to design a reward function for software or for something which is coded in the realm of what we can verify. Then rewards function are just success rates. But what happens when you don't have, when you want to express a reward function for how folded a t-shirt is? That's extremely complicated. You don't really have a way of doing that. So we're moving away from that and we're using demonstrations. What I mean by demonstration is something like the plot on the left side of the slide, where you have a trajectory, which is nothing but the recording of the actual motor's value when you're demonstrating, so when you're showing the robot what you want it to do. And at the same time, you also measure the observations. You also look at the camera frames. You try and match those two. And by trying and matching those two, you learn something which is a mapping between the two, and that's your behavioral cloning. That's your skill of learning how to reproduce human demonstrations. And if that wasn't good enough, then I should also mention that the amount of data that we're having that shows this demonstration is really on the rise. I want to show this. This is coming from a preprint that we're releasing super soon, which shows that not only you have large-scale data sets. When I say trajectories, I mean episodes, and the episodes is like minutes of data. And you have one of the largest scale data sets that was ever built, RT1, 130K episodes. That was more than 10x improved by OpenX, which is 1.5 million trajectories. Last month, lerobot, which is the library we're developing in Hugging Face, contained more than 3 million trajectories, completely open source. This is something which is already available out there. You guys can use it right now. And this is, of course, really, really, really useful if you want to do behavioral cloning, because you have a lot of data you want to learn on. Now, is that enough to build GPT-4? I wouldn't say that. That's orders of magnitude less, but it's definitely on the rise. And I want to touch on a bit of a technical detail because I wanted to give a bit more of a technical look. Sure, learning from demonstrations sound great. Don't do it supervised. Bad idea. Supervised learning for multimodal, complex distributions doesn't really work. You don't want to learn a mapping. You don't want to learn a deterministic mapping between a state and an action. You want to learn a generative model of the distribution. So you want to learn the joint distribution. I'm not talking about the optimizer that we're going to be using because that's a feud between me and Francesco, but the idea is that if you have a demonstration, if you have a set of demonstrations, those are non-IID data. There's nothing IID about why human moving an object. Like this movement depends on what I've done in the past, and that's really hard to learn. And also, what happens when you have a situation like the one in the robot? So you want to grasp the red cube, and you're starting from a position, and it's exactly the same if you want to go left or you want to go right, because there are no obstacles. Well, that's a multimodal distribution for you, because you can do two things which are equally as good. And how do you learn that using statistical learning? Well, that's a complex question, which people have answered in lots of really interesting ways. I'm going to claim that you shouldn't answer that question. You should just learn the generative model underneath it. And then I wanted to touch on something which is extremely recent. So all of this was, I guess, until 2024. It's already a paradigm shift in the sense that this is something which is changing in the context of robotics, but the new frontier is robotics foundation models. And robotics foundation models are targeting one specific problem. This is a slide that is telling you something is going wrong. We have small size crafted architectures that are great for performing one task specifically. We have siloed embodiment, meaning robot specific data sets. And as a result, we get task specific policies. We get something that if you want to switch on, if you want to go from grasping a glass to grasping a cup, or if you want to go to moving a chair from moving a car, that's entirely different. And you're going to have to retrain, recollect, and rebuild the entire system. This doesn't scale. People are working on robotics foundation models, which is using the large scale of robotics data we're getting right now, and the architectures are also standardizing. So we don't have small scale size task-specific architectures anymore. We're getting better at that. And that architecture is the VLA. VLAs are models that rely on transformers, and they're massively pre-trained amounts of data that allows you to build a hybrid model that is usually implemented as a mixture of experts, where you have one part of the model which takes care of perceiving the environment, and that's all it does. It takes frames as input, it takes a textual description of what you want to achieve, and then it extracts features that you can use to then learn something. And then there is another part of the model, which is where you learn how to actually act. And that part of the model is generative modeling powered in the sense that it uses flow matching, which you guys can think about as a variant of diffusion. And that's something that you do in order for you to learn an end-to-end model that takes care of perceiving but also acting. And that's the monolithic policies that I was talking about. Now, this concludes what I want to talk about in the sense that we're really building something at the interplay of control policies and interaction data, increasing interaction data, robotics, which is getting much more affordable, but the road ahead is really long. The robot is an end-to-end framework that is built for people to invite people to contribute. So please check it out if you want to get into robotics. That's a great starting point. The field is moving super fast, but we have an amazing team at Face which is building on top of this rapidly shifting environment, and I would definitely urge you to guys start contributing. That's a wonderful group of people. If you want to learn more, we're putting out a long-form tutorial that covers all of the topics that you need to know about for robot learning. This is coming extremely soon. This is you might notice, this is a screenshot from dated today because I was working on it earlier this morning. So you guys want to just follow us on Hacking Face on the Hub or on X, and we're going to be posting it once it's ready. With that, I think I went super over time. Thank you so much, and we'll leave questions for later.